Hey, today we're going to continue our discussion on conducting a hypothesis test for proportions. In the last class together, we talked about writing the hypotheses, and now we're going to talk about actually following through and doing a hypothesis test. So if you remember, we talked about this scenario where in this rural area, they drill wells, and they have 30% of them that find adequate water at a depth of 100 feet or less. And this other man thinks he has this method that will produce more wells, or a larger percentage of wells that are less than 100 feet deep in order to get adequate water. So we wrote the hypotheses for that together. Our null hypothesis, we presume that this man is going to be able to get wells, the same percentage of wells that are less than 100 feet as they would with normal drilling, so P equals 0.3. And then, of course, he claims that he can do better, that his proportion is going to be greater than 0.3, and so that's our alternative hypothesis. And so now we're going to conduct a hypothesis test. Much like with sampling distributions for proportions and means, in order to use the normal model, you have to satisfy assumptions and conditions. The same thing was true for confidence intervals for proportions and means. You must satisfy assumptions and conditions in order to use a normal model to assist you. And the same thing is true here for hypothesis tests. We're going to have to use a normal model in order to find probabilities. And so we need to satisfy these assumptions and conditions. And they're all the same, as we've seen. We need our data collected randomly, which did happen in this scenario. They sampled a random sample of 80 wells. We do need our independence less than 10% condition. We're just going to have to assume here that 80 is less than 10% of what this man has drilled. And we need to meet our success failure condition. So we need to have an expectation of getting 10 or more successes, 10 or more failures. And in this case, from our 80 wells, we would get 10 successes, or I'm sorry, 24 successes and 56 failures. An important thing to point out here, the P I used and the Q that I use come from my null hypothesis. So these values that we're using come from the null hypothesis. We are presuming that 30% of the wells will be drilled 100 feet or less. So we have to use that as our P, and same thing, we have to use 1 minus that as our Q. So we're going to be using our null value in these calculations. I guess that's not important now. So here's our hypotheses. Now we're going to calculate a standard deviation or standard error for our sample proportion. We have to use our null values here. So if you can see, I've used 0.3 and 0.7. We selected 80 wells, and so our standard deviation is 0.0512. Again, I'm using my null values. I'll type that again. And that's why in the equation you have that sub-zero for P and Q. That is related to the null hypothesis over here. So we're going to work with a normal model with mean 0.3, again coming from the null, and standard deviation that we just calculated, 0.0512. This is very similar to when we did a sampling distribution for sample proportions. So now we want to calculate what we call a p-value. So before we get our p-value, we're going to find our p-hat, which is 27 over 80. So we actually found 27 wells that were 100 feet or less out of the 80. So we get a p-hat of 0.3375. And our alternative hypothesis was greater than. So we have what's called a one-tail, right-tail test. We want the probability that our sample proportion is greater than 0.3375. So we can do a second vars normal CDF like we have been doing. My lower value is going to be this 0.3375. My upper value is going to be 1e to the 99. I'm going to plug 0.3 in for my mean and 0.0512 in for my standard deviation. And I'm going to get an answer of 0.232. That's what we call the p-value. I realize I made a mistake here. I want that to say 0.3375. I'm looking for the probability that my sample proportion is greater than the sample proportion that I actually got. So now we need to talk about what does this p-value mean. So this is a probability, this p-value. So it was 0.232, so approximately 23%, 23.2%. So that means that 23.2% of the time, if we took a sample of 80 wells, we would expect to see a result that we got, or a result that's more extreme. So more extreme in this case means more wells that are 100 feet or less, so a larger proportion. So there's a 23% chance of seeing the results that we actually got by sampling, or something more extreme. Again, more extreme being a larger percentage of wells that are 100 feet or less. So a pretty decent sized chance that if the true proportion is 0.3, that we would get a result that we got. Again, the entire time we're doing this hypothesis test, we're presuming that the null hypothesis is reality. 0.3% or 0.3 or 30% of our wells are 100 feet or less. So if that's true, 23% of the time, or a 23% chance, we would see the results that we got if that is actually true. So we've calculated a p-value. Now we need to make a decision about our null hypothesis. In our null hypothesis, we're either going to reject or we're going to fail to reject. This is just like saying somebody is guilty or not guilty. So if we have enough evidence to show that somebody needs to go to jail, then we say that they're guilty, and we would reject their innocence. If we don't have enough evidence, we can't show that that person's guilty, we don't say they're innocent, we say that they are not guilty, and that is the same as failing to reject our null hypothesis. We're not saying that that thing is true, because we don't know for sure, but what we're saying is we don't have enough evidence to show that it's not true. So we typically compare our p-value to this alpha level, and this alpha level can be different. We'll typically compare ours to an alpha level of 0.05. So we'll take our p-value and we'll compare our p-value to 0.05. So in our case, we're going to compare 0.232 to 0.05. If our p-value is less than 0.05, then we reject the null hypothesis. That means it's very unlikely, if the null hypothesis was true, that we would have gotten a sample result that we did. If our p-value is greater than this 0.05, then we'll fail to reject. That means there's a pretty decent chance that if our null hypothesis is real, that we would have still got that sample result. So in our case, we have a p-value that is greater than alpha. Our 0.232 is greater than alpha, so we're going to fail to reject our null hypothesis. We're not saying that it's truly 30% of the wells. We're saying that we don't have enough evidence based on our sample that that's different from 0.3. So we'll fail to reject our null hypothesis and conclude there's not evidence to show that Dowser's chance of finding water is better than normal drilling. So we've worked on writing the hypotheses. A lot of the process for making calculations is similar to what we've done before. This piece here, deciding to reject or fail to reject, is new. Our conclusion is new, and it takes some practice. So if you have questions or this wasn't clear to you, make sure you write them down so you can ask me in class, and we'll be definitely doing some of these together so that we can make sure we make the right decisions.